Okay. So this is our 318 lab project of PID controllers. Here we got me, Connor, Ian, and Brett. Do you guys like to introduce yourselves?
Ian Kebene.
Brett.
Okay. With the electric vehicles being the future of vehicles, we have to take into account that we need to control. We need control certain variables in these vehicles, including speed, turning, electricity to the motor.
So a customer needed a controller which can control the prototype of their car which to a desired speed. So to reach a desired speed, we came up with a prototype where it should have a minimum steady error, then comfortable acceleration, meaning that like the rise time in the graph should be almost 0.1 seconds, and then minimum fluctuation, that is the maximum overshoot, should not be fluctuating so much so that it can be also comfortable, and also the voltage should be less than 24 voltage. So yeah, that was the customer specification.
We use the equations of motion of an electric vehicle on a straight road, and the equations of motion for that are fairly simple model. And so using that, we are able to perform experiments on a rotating disk using angular velocity, and the angle traveled in a set amount of time. I mean, that's angular velocity. And so for the first lab, we modeled the mechanical parameters, finding the coefficient of viscous and dry friction and the torque constant. And then in lab 2, we modeled the electrical parameters for the setup, finding the relation of the DAC value to the motor voltage, and measuring the step response of the motor equation. In lab 3, we came up with the frequency response of the motor in Bode plot and modeled the proportional controller in the diagram. In figure 3, the diagram you can see on screen, and those are the two equations we used for it. In lab 4, we modeled the proportional derivative controller and tested it out. After that, we've found that the proportional derivative controller wasn't as it didn't reach the speed that we were looking for, so we used a low pass filter to help eliminate some of the noise, giving us a much smoother graph. And then after that, we did a proportional integral controller, which got us to the correct speed, but had a slower windup. And in lab 5, we tried to design a controller using the root locus and systool program in MATLAB to design the controller. Basically, we added zeros or deleted zeros, or added poles, deleted poles, until we got the output response that we were looking for. And this was our initial model setup.
All right, so as Connor and Ian had depicted, we had spent numerous weeks modeling and experimentally deriving numerous aspects of our controller. And ultimately, we were able to meet all the requirements as set forth by Solco, which was our customer. Now, there were a few assumptions and simplifications that we had to make, specifically mechanical systems. We assumed that the frictions associated with the mechanical systems stayed consistent throughout the entire life cycle of the component. That's not necessarily realistic, as bearing lubrication degrades and shaft surface finish changes throughout the life of the material. In the electrical systems, we also made some assumptions where Motor resistance would stay exactly the same throughout the life of the motor. Also not really realistic, especially if you take something like a brush DC motor, which the carbon brushes will degrade, get in the motor windings and actually add resistance, changing how that motor will operate over the course of its life. Next.
Experiment, it was very much an idealized system that we used.
So the advantages of proportional was like it improved stability and raised margin, good transit response, and also like it removed all offset error of the proportional controller and stabilizes the controller's gain. The trade-off, like the disadvantage was like slow time to stabilize than proportional only controller, and then integral wind up makes for slow response time. Order of the system is increased, causing the system stability reduction. So if we compare the controller comparison, so you can see that PI controller is better because it has like the rise time was increased, also settling time increased, phase margin decrease, and almost the even the overshoot. So when the overshoot increase, that means like it can get to the steady state error faster. So I think it was better, and it was better than the other ones.
So looking to the future, we're looking at ways that the PID controllers can be implemented in future technologies. And the first and foremost example that we're looking at is self-driving and autonomous cars. The way that these PIDs would work is like the example that this link had was self-driving cars and turning. So using PIDs to make sure that the car would maintain a constant trajectory while turning, making for a smoother ride for the passengers, which is, that's something that self-driving cars are aiming for, is to make sure that it is a good, safe experience for the passengers. And the PID controllers would help achieve that goal.